Part 1, we left off with 66, had been the last one I think we did. Ready for 67. Now we're getting into discussions that lead us to periodic trends in the table. And this first one is ionization energy. So this is basically definition. What do we mean by ionization energy of bromine? We always start with a gas. Remember why? Because you don't want to put energy into a solid or a liquid, because that doesn't tell you the whole story. I mean, you're wasting energy changing phases when you really want to know how much energy to promote an electron. So when we put energy into it, and most often it's heat, we're going to kick off one electron only. Still gas, and there's your free electron. So the one that looks like that, I think, is C. All right. That's 67, 68. And clear that off. I think I need to put up a periodic table and talk about the next ones. So this is the rough outline of a periodic table. Out there, across here, like this. That. And there's hydrogen, and there's helium. Sulfur, chlorine, and fluorine in this relationship, we want to order them by increasing ionization energy. Ionization energy increases from left to right and from bottom to top. So that means ionization energy is going to be that increasing ionization energy. And if we don't say first ionization energy, that's what we mean. If it's second or third, then we usually specify. So sulfur, chlorine, and fluorine. Where's fluorine? Well, let's see. Fluorine is going to be right up here. Right there's neon. So fluorine is going to be right next door. And then sulfur is going to be underneath oxygen. Oxygen's here. Sulfur is right here. Right? And then chlorine knows it. Yeah, chlorine is right next door. Okay, so if we're increasing ionization energy, we know fluorine is going to be the highest because of its position. Right, so it's greater than anybody. We just need to say which one of these. Well, sulfur is to the left of chlorine, so it should be less. So that should be the order. Sulfur, chlorine, fluorine. Increasing atomic radius. Right? We got the same ones? Yep, same ones. Okay, how does the radius change with position in the table? As you go across, the radius decreases because you're adding more nuclear charge, adding more protons, and the electrons that you're adding are in the same energy level. Right? So there's really no shielding going on. They're just getting drawn in by that increasing charge. So we're shrinking the atom size as you go from left to right. As you go from bottom to top, you're adding electrons to larger and larger shells. So the radius gets bigger this way or smaller that way. So the trend from lower left to upper right is decreasing atomic radius. Now that's just for neutral atoms. All right, when you start making ions, then it gets a little trickier. Okay, so if we're going to order them from increasing atomic radius, the bigger one should be this way, and the smaller one should be up here. So increasing atomic radius should be just the opposite. Let's see, this is 69. All right, chlorine and then sulfur. That's D. Yep, that's D. All right. 73. Let's see. I'll leave that up there for now. Just step aside. Of the following elements, which has the lowest first ionization energy? All right, so we got barium is roughly here. Let's remove that so we don't get confused. Barium's almost at the bottom here in the second column. And calcium is in the same column, but it's up here. Right. Silicon is over here underneath carbon, which would be about right here. That would be, let's see, 1, 2, silicon. This probably ought to be up a little higher. Who else? Phosphorus. Phosphorus is in the oxygen group under sulfur. No, it's in the nitrogen group. Okay, I'm getting kind of bunched up here. There's another column right in here, which is the nitrogens. So phosphorus, silicon, phosphorus is right here. And chlorine is already there. Okay, so back to the question. Lowest first ionization energy. Lowest would be right there, lower left-hand corner. How about of the following elements, which is most likely to form a negative ion with a charge of -1? Most likely to form a charge with a -1? Well, out of the ones that were given, would be the halogen, chlorine. Yeah, chlorine. Which of the following atoms has the largest ionization energy? Okay, so we got another set. Let's just clean this up. Start from scratch. So we need six. We need six over here. So let's see. If we do like this, and then split it. No, that's not it. We need to split the half into thirds. There we go. Now. Okay, so we got largest ionization energy. So we got oxygen, which would be right here. Lithium, neon. Neon's here. Lithium would be over here. Neon, beryllium. Beryllium's right next door. And potassium, which would be, skip sodium. Potassium's down here. Okay, so we're looking for the largest ionization energy. Oh, that's kind of a trick question. The noble gas is going to have the largest ionization energy because we're essentially taking electrons out of its core. It doesn't have any valence. Well, technically it does have valence, but the valence is full, so it behaves like a core. So neon would be the highest. Next highest would be oxygen. It's kind of a trick question there. See if your instructor's paying attention. 77. Which has these types of electromagnetic radiation arranged in decreasing frequency. So we're decreasing frequency or increasing wavelength. Works the same way. Okay, so let's just lay them out here and then we can work on what's given to us. So the lowest frequency, say the lowest frequency is to the right. So the longest wavelength and the smallest frequency, left to right. So how about energy? That would be smallest energy too, wouldn't it? Okay, just checking. Okay, so let's see. If we have the visible range in here, red is going to be on this side, longest wavelength. And this is going to be violet. So this is UV, this is infrared, radio, let's see, no, microwave, and then radio. Microwave, and then radio. And then this way, the next one below UV is X-ray. And then gamma. That looks too much like the there, gamma rays. Okay, now let's look at what we're given. Visible, an order of decreasing frequency. So left to right. Visible, ultraviolet should be on this side. It's not. It's on the wrong side. Okay, so A is not it. Radio, they'll go backwards. Right, so that ain't it. Ultraviolet, visible, and infrared. Ultraviolet, visible, infrared. That's the ticket. C. Let's see, 78. Oh, maybe I should have left that up there. Maybe we can do it without the line. Which of these arranged in order of increasing wavelength? Oh, same thing, right? Decreasing frequency, increasing wavelength. So C is the same. Decreasing energy, same thing. They're all saying the same thing in different ways. So we can move ahead with that one. How about number 80? In the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property? Okay, so N is the principal quantum number. Let's just review. And it's associated with energy and size. Okay. L is the angular momentum. Angular momentum. And it's associated with, let's see, shape. And M sub L is the magnetic. And it's associated with orientation in three-dimensional space. And then spins is all by itself. Okay, so if we're talking about magnetic, it's orientation. That's B. 81 is going to the angular orbital momentum quantum number, and that's shape. So that would be D. And let's see, go down to 84. Select the correct electron configuration for copper. All right. Copper has how many? 29. But notice the available answers are the abbreviated form. So we're going to go back to argon, which has 18. Then we're going to work from argon. So argon is in the third period. We're going to jump down to the fourth period and do our 4 S's. Then we're going to go to 3Ds. In 3Ds, we work across from scandium. 1, 2, 3, 4, 5, 6, 7, 8 is copper. 3D 8. Oh, wait a minute, that's not right. Did I count right? 1, 2, 3, 4, 5, 6, 7. Oh, 9. Sorry. This is what we would expect. This is one of the anomalies. The s orbitals can accommodate 2 electrons. The Ds can accommodate 5 shells, and we can have 2 each. So if we do this, 1, 2, 3, 4, 5, 6, 7, 8, 9, that leaves an odd number in one of these shells. And what we find is that the preference for these shells, subshells, orbitals, excuse me, that's a subshell, this is the orbital. For these orbitals is they either like to be half filled or whole filled. So if we had an element that only had 5 electrons in here, that would be perfect. But this one needs another one over here, and find that the energy level decreases if we steal one from here and complete that. So this is actually the copper configuration. 1 and 10. It's one of those, just one of those anomalies. You get a similar situation. Let's see. 18 and 10 is 28, 29. That's right. You get a similar situation if you're halfway across. Say scandium, titanium, vanadium, chromium. Chromium would be 24. And it would have 18 argon. And then it would have 4s and the 3ds. And it would prefer 5. It would prefer 1 here and 5 here, instead of 2 here and 4 there, which would give 24. So that's another anomaly. There's just something about, well, actually it goes back to Schrodinger's equations. And you punch in these quantum numbers, you find out that this arrangement gives you a lower energy than 2 here and 4 there. And it's not like we observe it firsthand. And there are other things that it explains better. All right, that's 84. These occur periodically in the table. Representative elements have their oddballs too. Let's see, 85. Which of the following equations correctly represents the process involved in electron affinity? Okay, we start from the same place with our element in the gas phase, neutral atom. Electron affinity, instead of like ionization energy, removes electron from a neutral atom. Electron affinity adds an electron to a neutral atom. So we're going to add an electron. And that gives us minus. Now, whereas the ionization energy required an input of energy, we get energy back from this one. So the delta H here is negative. It's an exothermic process because this electron is coming from infinity, comes down to some orbital in the atom, and gives up energy. So the more strong the affinity of the atom for electrons, the more negative the number. That kind of twists students' heads around sometimes. Okay, 85. No, we did 85. 86. How about that? That works better. Which of the following lists of atoms are arranged in order of decreasing atomic radius? Okay. Well, let's see. What do we have? Let's make room and put them here on our table so we can get an idea of what's what. Okay. So I'm just going down through the answers. Lithium, oxygen, nitrogen, and fluorine. So lithium is here. Oxygen is here. Nitrogen, yep. Nitrogen's here. Fluorine's there. And then lithium, nitrogen, fluorine. Sodium, strontium. So we got sodium down here. And we got strontium about down there. Oxygen, fluorine, we got that already. Calcium. Calcium is right here. And cesium down there. Sulfur. Sulfur is in this group right here. Sulfur and selenium underneath it. Okay. Those are all of our options. So decreasing atomic radius. They would decrease in this direction. So the biggest one is going to be cesium. Okay. Smallest one is going to be fluorine. That. And we can work, let's see. Yeah, left to right. Because when we move down to this level, let's see. Well, these guys down here are definitely going to be bigger than the rest. Strontium should be next. And then calcium. And there. Now we got a position. This one is on the level. Selenium's on the level here. Selenium is smaller than calcium. Yeah, selenium is smaller than calcium. And then we can come up here to sodium because it's in a smaller energy domain. We'll just see how lucky I get at these. And then sulfur. Let's stretch that out a little more. And then lithium, nitrogen, and oxygen. Now we can go to our availables and let's see. Lithium, oxygen, nitrogen's backwards. So A is not it. Lithium, nitrogen, oxygen, fluorine. That's a good group right there. For B. We went to the others. Fluorine, oxygen is backwards. Sodium, strontium. That's backwards. And calcium, cesium. That's backwards. So I think we got our best choice with B. All right. I've got a little math coming up here. '87. Consider atom traveling 1% speed of light. The de Broglie wavelength is found to be 1.46 times 10 minus 30 picometers. Which element is this? All right. I'm going to have to cheat so that I don't waste your time. 87. Let me just take a peek at it and refresh my memory. Okay. Yeah. All right. The combination of Einstein and Planck. And Planck would be this one. Or if we have to go with wavelength, which we do, then it would be this and then the over wavelength. There we go. Okay, now to answer the question, we need information about the element, either the atomic number or the molar mass. I don't think we can get the atomic number out of this information, so we're going for molar mass. So molecular weight requires that we know the mass per unit mole. All right. And okay. We're talking about one atom, then we can work with moles because we can change that one atom to what fraction of a mole it is. We need to find out what the mass is. Well, de Broglie says that we can take this equation and instead of using the speed of light, which is only good for light, we can substitute the velocity of any particle. So de Broglie says we can do this. Okay, and substitute any particle we want in there. All right, so if we're looking for mass, then we want to take this equation and put it in here somehow. Well, energy, that's the common variable here. So this is going to be equal to that energy expression. Like that. And then we can solve for mass. Mass equals, hc over lambda v squared. Okay? All right. Let's see. This is a constant. Oops. Okay, this is a constant. This one changes with the speed of the object, which is 1% of the speed of light. So what's 1% of the speed of light? 2.9979 times 10 to the 8th meters per second. 1% of that is times 0.01, isn't it? Okay, so that's 10 to the minus 2, which would make this 10 to the minus 6. 2.9979 times 10 to the 6th meters per second. So that goes in right here. Okay, how about wavelength? 1.46 times 10 to the minus 3 picometer. 1.46 times 10 to the minus 3 picometer. So what's a pico? Let's see. Nano is 10 to the minus 9th. Pico is 10 to the minus 12th. So 10 to the minus 12 times 10 to the minus 3 is 10 to the minus 15. So this velocity, this wavelength here is 1.46 times 10 to the minus 15 meters. These have to be in SI units to work, right? And let's see, what's 6.626 minus 34? 6.626 times 10 to the minus 34 goes here. And this, of course, is 2.9979 times 10 to the minus 10 to the 8th, 10 to the 8th meters per second. Let's see, we covered all our bases. Yep. And that should give us a value of mass in kilograms, right? SI units. Do my calculator. Here it is. Okay. So 6.626 exponent minus 34 times speed of light and divided by that many meters. And then we got to square this one. 0.9979 exponent 6. And then square it. And divide that into it. So that gives us equals 1.51. That's good enough. Times 10 to the minus 23 kilograms. Right? We're going to calculate the molar mass. We need grams. So kilo is 10 to the third, isn't it? 10 to the third times minus 23rd is 1.51 times 10 to the minus 20 grams. So that's what goes in here. Now we need to find out how many moles does that represent? Okay. So how many moles is that? Well, one atom needs to be converted to moles. 6.022 times 10 to the 23rd atoms per mole. So we just take the inverse of this value. Inverse. And I get 1.66 times 10 to the minus 24 moles. Okay, so this right here is divided by that, according to that formula, grams per mole. And let's see, oh, they're in my calculator just right, except for this one. That one needs to be times 1,000. And then flip them and divide. Yeah. So that's, whoa. I don't know any elements that have that kind of mass. So I made a math error somewhere.
There you squared velocity, but on the word problems, you did not.
Oh. Okay, hold on a second. Mass. Oh. Okay. I see what I did. It should have come out okay, but what I actually did was I left this as C, right? Like that. Is that right? Yeah, no, C squared. So that means this cancels and that cancels. So we have Planck's constant divided by the wavelength divided by the speed. Then we change this over to V. So let's see what that gets us. Am I going in the right direction? Okay. Then 1.46 exponent 15 divide and 2.9979 exponent 6 divide. Okay, so this gives me minus 25 kilograms, and that means this is going to be 22. Okay, I decreased that one by what? 2 or 3? Well, I'll just put them in again. 1.51 exponent negative 22, and then 66 exponent negative 24. And that's roughly 91. 91 grams per mole. What's close to that? Zirconium, right? Yeah, I changed my variables too soon. We needed to reduce the equation, and then instead of the speed of light, we would use the speed of the particle. It should have worked both ways, I think. Well, anyway, rather than dwell on that one, we'll move on. 88. All right. In an investigation of electronic absorption spectrum of a particular element, it's found that the photon having wavelength 500 nanometers provides just enough energy to promote an electron from the second quantum level to the third. From this information, we can deduce what? Okay, so if we've got an atom here, and we've got 1, 2, 3, 2, 3. Promote an electron from the second level. Yeah. So this electron is here. It's going to go from there to there, and it absorbed enough energy at 500 nanometers. Okay, what does this tell us? The energy of the N2 level? No. Energy of the N3? Nope. Tells us the difference. Not the sum of the energies. It tells us the difference between this energy level and that energy level. Okay, that's why D. Now we do have a formula that we can calculate this one and that one, but this amount of energy is related to the jump, not to the stationary position of the electron. Speaking of which, 89. Let's see. We don't even have to calculate the energies. They're given to us. So we're dealing with a hydrogen atom, and the energy at each of the levels, notice that they get more negative as you get closer to the nucleus. That's because when you add enough energy to promote that electron to infinity, it takes that much energy. To go from N, you have to put in an equal and opposite sign energy of 2.178 times 10 to the minus 18 joules. That will take it to zero energy, which is infinity. So that's why they're negative. They get more negative as you get closer. They're lower energy. Okay, back to the question. What is the wavelength of light associated with N3 to N1 electron transition? And what we're saying here is that we're not paying attention to the sign. We're just saying, what's the difference in energy between the two levels? And that photon could either be promoting the electron up, or it could be giving up if the electron drops. So we're going 3 to 1. Okay, if we are going from 3 to 1, then okay. So the energy transition is equal to final minus initial. So 1 is minus 2.178. 178 times 10 to the minus 18. And then minus 3, right? This is final, and this is initial. That's the way we always calculate differences. And this is 1, this is 3. Minus 0.0240 times 10 to the minus 18. Okay. So let's see, we got 2.178 and change the sign. I'll keep the sign for now. This is becoming a positive. 0.020. No, 0.0240 plus. Okay, so the difference is a negative 2.154 times 10 to the minus 18 joules. And if we just want to know the energy transition, we'll take the absolute value of that. And we find that if we're looking for wavelength, okay, wavelength, that means we need energy equals Planck's constant. Planck's constant, and then speed of light over lambda. Yep. Okay, so if we put the values in here, 10 to the minus 34 joule seconds for Planck's constant, and then 2.9979 times 10 to the 8th meters per second. And then wavelength is our unknown, right? Because this is equal to that. And we're going to take the absolute value. So just change the sign. There we go. So I got that one. And actually, this comes over here, and that goes over there. I just swap places with them to solve for the lambda. So that means 2.9979, 0.8. We flip those because I want to divide. And then 6.626 exponent, 34 times. And I get the energy, excuse me, the wavelength. I don't like that looks of that. Let me try it again. 6.626 exponent 34. And then 2.9979 exponent 8. And divide by 2.154 exponent. That's better. So the wavelength in meters, 9.22 times 10 to the minus 8 meters. Now, we're in nanometers, centimeters, and meters. All right, do we have one in meters like this? No. We don't have any of them like that. Where did I go wrong? Maybe this one? Let's see, final is minus. Yep. It went from 3 to there. Oh. There's the problem. Like it's 2420. Let's try it again. 0.78.242 1936. 1936. 10 to minus 18. So this goes down. This goes over here. Now we're going to put it over there. Let's have 9 exponent 8, and then 1.936 exponent 10. Divide 6.626 times. Okay. 1.026 times 10 to the minus 7 meters. Oh, round it off. All right, 1.03 10 to the minus 7 meters. That's why E's the answer. I just made a math error. Actually, it's necessarily math. I misread it. Yeah, I misread it. I put a 0 in there. It shouldn't have been 1. Okay. Oh, we got another one. It goes from 5 to 1. So there's 1. Now we'll go to 5, which is 0.8712. 0.08712. That's going to change this value and this value. Okay. Eight. 2. Okay, this is negative 2.09088. Okay, and then that's going to be divided into this number times Planck's constant. So I get 9.50 times 10 to the minus 8 meters. Yeah, that's B. Looks good. Right. Moving on. Hope I don't need that again. Let's see, 91. Which of the following is reasonable criticism of the Bohr model of the atom? Okay. A, B, C, D, and E. How about A? Makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Makes no attempt to explain why the negative electron does not fall into the positive nucleus. That's a reasonable criticism. It makes no attempt. It can't explain it. Well, now I'm puzzled. What does B say? It does not adequately predict the line spectrum of hydrogen. No, it does. Right. So that one's good. It does not adequately predict the ionization energy of the valence electrons for elements other than hydrogen. Well, that's, yeah, there we go. does not adequately predict the ionization energy of the first energy level electrons for one electron species for elements other than hydrogen. Now it does that. All you have to do is make it look like hydrogen. And then the formula takes account of the number of protons you have. Right. So that's not that's not a reasonable criticism. Shows the electrons to exist outside the nucleus. Well, that's okay. So it's a toss-up between A and C. Maybe I worded it wrong. What does your copy say for A and C? Is the wording wrong if A said it makes an attempt to explain why the negative electron does not eventually fall, then that would be it makes an attempt. No, that would be it doesn't make an attempt. Okay. I don't like that question. Will not. Hopefully you won't see that one again. But we did get to talk a little bit about the Bohr model. It's basically planetary, saying the electrons, orbit the nucleus like planets. But we found that to be wholly inadequate. Which of the following statements is true? All right. 1, 2, 3, 4, and 5. Correct. An excited atom can return to its ground state by absorbing electromagnetic radiation. That's false. It gives up energy when it does that. The energy of an atom is increased when the electromagnetic radiation is emitted from it. No, it's decreased. Right? You have to conserve energy. So if it gives up energy, the atom itself has to decrease in its energy state. That was false. The energy of electromagnetic radiation increases as its frequency increases. Yep, that's true. Right? Planck's constant. Planck's law. An electron in the n equals 4 state in hydrogen can go to the n equals 2 state by emitting electromagnetic radiation. Yes, it can. Going from a higher state to a lower state has to give up energy. And then 5 says the frequency and wavelength of electromagnetic radiation are inversely proportional. Yep, that's true. Oops. There. Oops. That's not right either. There we go. So 3, 4, and 5 are good answers. 94. Consider the following representation of a 2p orbital. Okay, yeah, it's kind of like, I like to draw them like that, but that's okay. Which of the following statements best describes the movement of electrons in a p orbital? Okay. A, B, C, D, and E. The electrons move along the outer surface of the p orbital similar to a figure 8. I don't think so. No. What that shape expresses is the probability of finding an electron in that space. The electrons move within the 2 lobes of the p orbital, but never beyond. They could be further from that. This is just the highest probability, right? You could have an electron out here, but it'd be very low probability. And that stems from the Heisenberg uncertainty principle. If you know where the electron is, then you can't tell what its energy is, and that doesn't do us any good. Right? We want to know what the energy is, and we'll say it's most likely to be there. That's far more useful. C, the electrons are concentrated at the center node of the two lobes. No, that says there's no probability of finding an electron there. Electrons are only moving in one lobe at any given time. And E, the electron movement cannot be exactly determined. There's the ticket right there. That goes back to Heisenberg. You can't determine the electron movement. Not for something that small. Oops. Okay, 95. How many electrons can be contained in all of the orbitals with n equals 4? Okay. L can be 0, 1, 2, or 3. Right? M sub L can be 0. Right? This one can be -1, 0, +1. This one can be -2, -1, 0, +1, or +2. This one can be -3, -2, -1, 0, or +1, +2, +3. We're counting the total number of electrons. Possible, how many can it contain? So we got 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Got 16 positions times 2 electrons equals 32 electrons. There used to be a formula. Hmm. I can't remember what it is. It might be in your textbook. But this is the foolproof way of figuring it out. I also test whether you know how to do all that stuff. Uh, 96. Let's see, the small but important energy difference between 3s, 3p, and 3d orbitals are due mainly to penetration effect. Right? Because you're going to have, at level 3, you're going to have the biggest node for the biggest population of S electrons is going to be out here somewhere. But it's got a node there, and it's got a hump there and hump there, and 2 nodes. And the p orbitals are going to be kind of in here, but it only penetrates that far. And then the d's are going to be actually they're not there. I'm sorry. D's are going to be in here like this. So the penetration effect gives a higher probability for the S than it does for the P and than it does for the D. That penetration effect. Okay, 97. Which of the following was not an elemental property usually predicted by Mendeleev for unknown elements? Well, electronic configuration for sure. He had no idea about the structure of the atom. Yep. Atomic mass, yep. Density, boiling point, oxide formula, yep. Oxide formula was a very common way to describe elements in those days. That's where oxygen group gets its name. The chalcogens, based upon the formation of a calx with a metal. It's a metal oxide is called a calx. So they named that group after, chalcogens. Gen means to create. So it creates a calx. Okay, so moving on, 98. And we still live with that historical oddity, even now. When you see the numbers on a fertilizer bag, like 10, 10, 10, right? This is going to be nitrogen, just pure nitrogen by mass. This is going to be P2O5. This is going to be K2O. So we report these two for those elements as oxygen derivatives, oxygen compounds. So if you ever want to do any calculations with those values on the bag, you got to take that into account. How about 98? I already got it up there. Which of the following atoms or ions has 3 unpaired electrons? All right, 3 unpaired electrons. So if we look at nitrogen, oxygen, aluminum, nitrogen, oxygen, aluminum, and then we got a couple of ions, sulfur, 2-, and titanium, 2+. Okay, so the nitrogen we know is going to be its highest energy level is going to be 2p. Okay. So its 2p is going to be like this with 3 unpaired electrons because of its position there, right? Boron, carbon, nitrogen, 3 electrons in the p orbitals, and that's the way they have to go in. So that's a good answer. Oxygen's to the right, so it's going to have an extra one. Okay. Aluminum's to the left, it's only going to have 1. These are all 2p's. Right? Sulfur 2- is going to take on 2 extra electrons. So its p orbitals are going to be like this, 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 and this. It's going to be full. It's going to look like argon. Okay, dilution? No, okay. Titanium 2+. So that's going to have 3D. These are 3D right here. And it's only going to have 2 electrons. That's it for titanium. Oh, wait a minute, it's 2+. It's not going to have any. It lost them both. Sorry. Yeah. It's going to have a full 4s, but titanium could be 2+ or 4+. If it lost those 2 s electrons, then it would look like argon also. So that's why we get 2 possible charges for titanium. One by losing the 3Ds, and the other by losing the other 2 4s's. So it can be either 2+ or 4+. Okay, 101. For some reason, this question really messes with students' minds, and I never have figured out why. 101. An element E has an electron configuration of, okay, so this E has krypton. Let's go ahead and put 36 electrons here. 36 has 5s2 and 4d10. 5s2, 4d10, those are filled. And then it has 5p2. Okay. So, what are the possibilities here? Well, this can either be, if it loses those 2, which is preferable, then it could be a 2+. If it loses these two, because these are at the same energy level, it would have to lose these two. It could also be a 4+ ion. So when we combine it with fluorine, it could either have two fluorines, right? Because each one is a -1, or it could have 4 fluorines to make up the difference. So that's why B is the best answer out of that group. Okay? All right. Maybe this class is going to be an exception. All right. 104. See how we're doing on time. 140. Oop, I got 4 minutes. Which of the following atoms would have the largest second ionization energy? A, B, C, D, and E. So we have magnesium, chlorine, sulfur, calcium, sodium. So to simplify things, the second ionization energy, I should put it this way, that's not right. The second ionization energy versus the first. If you have any with 2 electrons in their valence shell, then their second ionization energy is only going to be about double the first. Right? Magnesium would fit that. It has 2 electrons in its outer shell. It's 3s2. Let's just do that. 3s2. Chlorine is 3s7. Sulfur is 3s6. Calcium is 4s2. And sodium is 3s1. If you get rid of this one, right, second one's going to be down in the core. These are still going to be, second one is going to be in the valence shells. So this one is the highest second ionization energy. Also because it's the highest up here, plus you're getting into the core. Right. Once you get into the core, things jump an order of magnitude. That was the whole point of that question. All right. 107. Which of the following concerning second ionization energies is true? All right. That the second ionization energy of aluminum is higher than that of magnesium because magnesium wants to lose the second electron. So it's easier to take the second electron away. Well, the second ionization energy should be higher for aluminum, but not for that reason. It's higher because aluminum has more protons. Right? So that's why this one's false. That's not a good explanation for it. Aluminum is higher than that of magnesium because the electrons are taken from the same energy level, but the aluminum atom has one more proton. There you go. That's true. And do we have any wonky ones in there? No. We found our answer. Interest of time, we're going to move on. 108. Consider a planet where the temperature is so high that the ground state of an electron in hydrogen atom is N equals 4. What's the ratio of the ionization energy for hydrogen on this planet compared to that of Earth? Okay, so if we have, this is our planet, this is Earth, and we have a hydrogen atom here with N equals 4. N equals 4 ground state. Whereas on Earth, hydrogen N equals 1. Okay, so the ratio of the ionization energy from hydrogen on this planet compared to Earth. So we want the first ionization energy from this planet versus the first ionization energy on Earth. Okay, if you're going from 1 to infinity, this ionization energy is going to be higher. That's qualitative expression, right? You're promoting an electron from N equals 1 to infinity. Whereas you're going from N equals 4 to infinity, takes less energy. It's already got some energy added to it. Okay, now what we need to do is quantify that. So if the ratio, we want the ratio of the planet energy to that one. So this is going to be the lesser number to that one. That means A or C is about the only one. They're not going to be equal. All right, so it's either A or C. And what we need to do is look at the expression of the how we determine the energy levels, which is, let's see, useful information. Looking for that equation. There it is. Equals Z squared over N squared. We got a number in here, and then we got Z squared over N squared. So that number is gonna cancel out anyway. What we want to do is ratio these two. So if we put this one is going to be this is going to be 1, right, for both of them. So this is the key right here, that N. So this is going to be 4, like 1 over 4 squared. And this is going to be 1 over 1 squared. So the difference in energy, actually, to find the difference, we need to go from here to infinity. And infinity, we need to add another term out here, whatever that infinity is. So what we're talking about is this energy level is going to be bigger by a factor of 16. That's what we're saying. So actually, the ratio is takes 16 times more energy on Earth than it does on this planet. I've never explained it that way before, so I hope it works. I think in the work problems, I actually I do the math. And that can get kind of hairy. I was hoping that this would be a little easier to understand. We got any more? Or is that it? I think that's it. We're done. Unless you have questions. Okay, so this is Thursday. We'll be looking at an exam on Tuesday. Yeah. Tuesday, and we'll jump into chemical bond, chapters 8 and 9, the last ones in the coming down the home stretch. And we'll have separate exams on bonding. The first one is essentially going to be, well, the second one's going to be molecular orbitals. First one's going to be on ionic bonds and the valence bond theory.